Fatty acids are part of the family of lipids that serve as the main storage of fuel. Most tissues can oxidize fatty acids for energy except for red blood cells, which don't contain mitochondria, and cells of the central nervous system, where fatty acids can't cross the blood-brain barrier. Interestingly enough, cardiac muscle uses fatty acid as the primary source of fuel, which explains why diseases of fatty acid metabolism can affect the heart, but we'll save that for another time. In this sketch, we'll grab a bite at Sketchyland Pizza to understand triglyceride catabolism and beta-oxidation of even-chain fatty acids. Boy, do I love pizza, and I'm sure you do too. Come and try a delicious, greasy, cheesy carnitas pizza as you sip on some cool, refreshing acetyl cola. Your gallbladder will love it as much as you do, and that's a guarantee. The sitting area of this restaurant looks an awful lot like a mitochondrion, which is convenient, because beta-oxidation of most fatty acids occurs in the mitochondria. What about those very, very long fats? Well, they're actually oxidized in peroxisomes. We've illustrated some very long zigzag salami next to an H2O2 bottle. Remember, that bottle of hydrogen peroxide is our recurring symbol for peroxisomes. Most fatty acids are stored as triglycerides in adipose tissue. When blood glucose levels decline long after a meal, hormone-sensitive lipase hydrolyzes triglycerides into glycerol and free fatty acids. We've included glacier gum and 3 zigzag pizzas to show the products of triglyceride catabolism, glycerol and free fatty acids. You're probably wondering how hormone-sensitive lipase is regulated. Insulin, glucagon, and epinephrine are the main hormones that control hormone-sensitive lipase. In the setting of low insulin, glucagon and epinephrine will activate hormone-sensitive lipase. See the kid cutting the cheese? Not that cheese. Gross. He's wearing an Epic apron to remind you of epinephrine. What about glucagon? Well, how about some glucagon sweetener to go with that cheese? No? All right. Maybe next time. Also on the counter, you'll see candies inside a liver-shaped bowl and another pack of glacier gum. Besides making triglycerides, glycerol can feed into gluconeogenesis. Please check out our Davy Jones's Candy Locker sketch to learn more. Okay, we can finally go over the pathway. Please don't hesitate to pause or rewind the video to review this diagram anytime during the sketch. Fatty acids must be activated before they enter the mitochondria. Acyl-CoA synthetase uses ATP to make fatty acyl-CoA from a free fatty acid and CoA. The worker using an ATP-powered drill to fix the menu board is acyl-CoA synthetase. The menu board contains a zigzag pizza and cola. They represent the substrates free fatty acid and CoA, respectively. When they combine, they make fatty acyl-CoA, or for our purposes here, a zigzag pizza and cola combo meal. Long-chain fatty acyl-CoAs can't directly cross the mitochondrial membrane and must rely on the carnitine shuttle. The long carnitas pizza being passed across the counter will help you remember that carnitine is needed to transport long-chain fatty acids into the mitochondrial matrix. The carnitine shuttle contains 3 proteins: CAT1, CACT, and CAT2. Carnitine acyltransferase 1, or CAT1, substitutes CoA with carnitine to make fatty acylcarnitine. Just think of Caddy adding carnitas to that pizza and removing cola from the tray. Caddy is standing outside the mitochondrial dining area because CAT1 is found in the cytosol. Also because it's considered tacky to put toppings on the pizza after you serve it. Malonyl-CoA, a substrate for fatty acid synthesis, inhibits CAT1. Why? Because we can't make and break down fat at the same time. Would you ride your bike while tying your shoes?
I would.
Shut up, Chad! Anyways, looks like some melon cola spilled on poor Caddy. The melon cola is malonyl-CoA. Now, I don't know about you, but a spill will inhibit me from doing anything. Maybe I'm just lazy, though. In the next step, carnitine acylcarnitine translocase, or CACT, transports fatty acylcarnitine across the mitochondrial membrane. The waiter passing the carnitas pizza across the counter is CACT, but I'm sure his cactus flare pins gave that away. Okay, the final player in the carnitine shuttle is CAT2. CAT2 turns fatty acylcarnitine back into fatty acyl-CoA. You'll see Catherine, another waiter, remove carnitas toppings from a pizza because apparently the kitchen got the order wrong. Awkward. She's also adding a complimentary cola to the tray to atone for their sins. She's cat 2, by the way, if you didn't catch all that. Now that fatty acyl-CoA is inside the mitochondria, we can finally start beta oxidation. Quick breather before we dive back in. And before we go over the steps, keep it in the back of your mind somewhere that we make one FADH, one NADH, and one acetyl-CoA for every round of beta oxidation, assuming we're dealing with unbranched, saturated, even-chain fatty acids. All right, break's over. Let's do this. Beta oxidation is broken into 4 steps. First, acyl-CoA dehydrogenase oxidizes fatty acyl-CoA to enoyl-CoA while making one FADH2. This enzyme will be represented by the customer wearing a towel bib about to gorge on some pizza and cola. We've also included an FADH2 energy bar because we make one FADH2. The product is enoyl-CoA, or simply an oily pizza plus cola. In the next step, enoyl-CoA hydratase adds water to enoyl-CoA, making 3-hydroxyacyl-CoA. The customer splashing some water onto the oily pizza will help you remember that enoyl-CoA hydratase adds water to enoyl-CoA to make 3-hydroxyacyl-CoA. Do you see that gross watery pizza, OH cup, and cola? Yep, that's 3-hydroxyacyl-CoA. Let's get to the next step where 3-hydroxyacyl-CoA dehydrogenase oxidizes 3-hydroxyacyl-CoA to 3-ketoacyl-CoA while making one NADH. We drew a napkin drying the watery pizza to show 3-hydroxyacyl-CoA dehydrogenase. Note the NADH energy drink because we make one NADH. The product is 3-ketoacyl-CoA, represented by the cola cup, pizza, and key-shaped pizza cutter. Finally, in step 4, thiolase cuts 3-ketoacyl-CoA into 2-carbon acetyl-CoA and makes a smaller acyl-CoA with 2 fewer carbons. The waiter cutting the pizza is thiolase. You can tell because he's got a knife on his thigh. Boom! Memory bomb. For fatty acids with an even number of carbons, these 4 steps repeat until we're out of carbons. To calculate the number of acetyl-CoAs you'll get from an even-chain fatty acid, divide the number of carbons by 2. To calculate the number of FADH2 and NADH, subtract 1 from that number. For example, palmitic acid, a 16-carbon saturated fat, will make 8 acetyl-CoAs, 7 FADH2, and 7 NADH. In contrast, fatty acids with an odd number of carbons will undergo the same 4 steps of beta oxidation until we're left with 3-carbon propionyl-CoA. Propionyl-CoA is metabolized differently, and we'll cover that process in a separate sketch. Okay, so we've made acetyl-CoA. What happens next? Well, it can enter the TCA cycle. Alternatively, when blood glucose levels are low, like during a prolonged fast, acetyl-CoA cannot enter the TCA cycle because oxaloacetate is depleted. Instead, acetyl-CoA is used to make ketone bodies. Please watch our ketone body sketch for more information. And be sure to grab a candy key on your way out. Had enough pizza? Let's get out of this restaurant. But before we go, most fatty acids undergo beta oxidation in the mitochondria, except for the very long-chain ones, which are broken down in peroxisomes. Fatty acids are primarily stored as triglycerides in adipose tissue. Hormone-sensitive lipase hydrolyzes triglycerides into glycerol and free fatty acids. Glucagon and epinephrine activate hormone-sensitive lipase. After generating free fatty acids, acyl-CoA synthetase uses ATP to turn them into fatty acyl-CoA. Long-chain fatty acyl-CoAs can't directly cross the mitochondrial membrane and need to go through the carnitine shuttle, which consists of CAT1, CACT, and CAT2. CAT1 turns fatty acyl-CoA to fatty acyl-carnitine, CACT transports fatty acyl-carnitine across the mitochondrial membrane, and CAT2 turns fatty acyl-carnitine back into fatty acyl-CoA. Once inside the mitochondria, we can start beta oxidation. First, acyl-CoA dehydrogenase oxidizes fatty acyl-CoA to enoyl-CoA while making one FADH2. Next, enoyl-CoA hydratase adds water to make 3-hydroxyacyl-CoA. Then, 3-hydroxyacyl-CoA dehydrogenase oxidizes 3-hydroxyacyl-CoA to 3-ketoacyl-CoA while making one NADH. Finally, thiolase cleaves 3-ketoacyl-CoA into 2-carbon acetyl-CoA while generating a smaller acyl-CoA with 2 fewer carbons. These 4 steps are repeated as necessary until we're out of carbons. Acetyl-CoA, one of the end products of beta oxidation of fatty acids, can either enter the TCA cycle or be used to make ketone bodies.